In June 1944, the battlefields of the Southwest Pacific glimmered with the metallic shine of thousands of daily sorties. From forward airfields in New Guinea, formations of P-38 Lightnings of the U.S. Army Air Forces flew north to support ground units advancing under General Douglas MacArthur's plan. The Back to the Philippines campaign required control of airspace extending over 500 miles, beyond the safe operational range of any heavy fighter at the time. According to the 9th Air Force reports, each long-range bombing mission consumed nearly 1,000 gallons of fuel, while the P-38 carried only about 410 gallons internally and two 150-gallon drop tanks. Pilots often returned with fuel gauges hovering at the red line. Many disappeared over the sea due to headwinds or detours around storm clouds. Their worst nightmare came not from flak, but from the steadily falling needle on the fuel gauge. According to the 475th Fighter Group's records, in the second quarter of 1944, they lost nearly 12% of their aircraft not to enemy fire, but to fuel exhaustion or disorientation after flying more than 600 miles. This limitation made the P-38 a double-edged sword, powerful and fast, yet constrained by its own fuel consumption. The engineering teams at Hollandia tried everything from replacing heat-resistant spark plugs and fuel filters to altering the oil mixture ratio, yet none improved its range. Amid the humid air and heavy smell of fuel, people began to accept that a 570-mile limit was the aircraft's destiny. But at the strategic level, that limit was dangerous. According to an analysis by the Southwest Pacific Area Command to support the upcoming amphibious landings, the fighter squadrons had to protect both bombers and landing ships within a radius of at least 750 miles. MacArthur needed air cover to lead the advance, but calculations showed the current fighter groups had just enough fuel to reach the target, engage briefly, and return. No planner could guarantee survival if the weather turned bad. The core problem was not firepower, it was energy efficiency. While officers debated over maps and measuring tools in the operations room at the Satan's Angels squadron camp in Hollandia, the 26th of June 1944 began like any other day. P-38Js stood in rows on the red dirt, their metal skins glinting in the sunlight. Colonel Charles MacDonald was playing checkers with Merrill Smith, a half-burned cigarette in his left hand. The door opened, and a tall, lean man in a khaki shirt stepped in, his voice calm and steady. "I'm Charles Lindbergh." The room fell silent. The name was too familiar. The man who had crossed the Atlantic alone in 1927, a symbol of America's golden age of aviation, now stood before them not in uniform, not wearing insignia. According to MacDonald's journal, his first reaction was confusion. We were at the front lines, and he, a civilian, said he wanted to help improve P-38 performance. Normally, such a request would have been rejected outright, but Lindbergh hadn't come to lecture. He asked for permission to fly along, to observe real operations. His papers, issued by United Aircraft, authorized him to act as a technical consultant in the theater. Behind that document lay Washington's silence. Roosevelt had forbidden him from rejoining the military after his anti-war speeches 3 years earlier. Now he came under the title of an expert, nothing more, nothing less. The young pilots of Satan's Angels talked about it all afternoon. Many doubted that a 42-year-old man who had never flown in combat could understand the pressure of battle. Some were excited to meet the legend they had read about in books. As for MacDonald, though skeptical, he agreed to let him fly on the next morning's mission. "If he wants to see reality, I'll show him reality," he wrote in his flight log on June 27. That night, in the field hut, Lindbergh sat alone by an oil lamp, reviewing the P-38 Jules's fuel consumption charts copied from Lockheed's manuals. He underlined the figure 100 gallons divided by hour, standard cruise, and wrote beside it, "Surely wrong." As the sound of frogs and generators mingled, he pulled out a slide rule and calculated, his eyes pausing at one line, 1,600 revolutions per minute, 30 inHg, 70 gallons per hour, 2.6 miles divided by gal, a small, neat note that could change the entire air strategy in the Pacific. According to the 475th Fighter Group's report preserved at the Air Force Historical Research Agency during Lindbergh's very first mission, his P-38 returned with 20% more fuel remaining than his squad mates. The technicians thought the gauge was broken. No one believed that a minor adjustment to RPM and mixture ratio could save hundreds of gallons. But the numbers didn't lie. That day, Hollandia was still full of engine noise and fuel smoke, but amid the chaos, a simple data point had appeared. It bore no rank, appeared in no flight manual, yet later it would redefine the range of American fighter aircraft. As night fell over the airfield and the pilots returned to their tents, Lindbergh kept writing. He recalculated each figure, comparing it to the day's results. Outside, rain drummed on the tin roof. For a brief moment he stopped, looked toward the dimly lit airstrip, and murmured almost to himself, "The power of this war lies not in bullets, but in data." And on that quiet, rainy night, the revolution of numbers began. To understand how a civilian could change the entire flight doctrine of the United States Air Force, we must return to a morning in May 1927, when the spirit of Street Lewis left the runway at Roosevelt Field. Cold Atlantic winds swirled around the fuselage, curling past the asymmetrical fuel tanks packed so tightly they blocked his forward view. Charles Lindbergh, then only 25 years old, carried 450 gallons of fuel and the conviction that every calculation must be proven by reality. He had computed every pound of gasoline, every knot of wind, every percentage of mixture. After 33 hours, 30 minutes, and 3,610 miles, he landed at Le Bourget with 85 gallons remaining. According to the technical log he kept, the average consumption was only 365 gallons. That figure astonished the Rolls-Royce engineers, as the Whirlwind engine was not believed capable of such efficiency. Lindbergh had proven the opposite. Flight performance did not come from intuition, but from empirical data. Those numbers became his lifelong obsession. During Pan American Airways survey flights in the 1,930 seconds, Lindbergh spent hours before the instrument panels, recording correlations among revolutions, manifold pressure, and altitude. He discovered that each engine possessed an optimal operating range where power, temperature, and fuel consumption reached equilibrium. He called this the optimum cruise envelope. According to the Pan Am Engineering Memo 1933, Lindbergh tested more than 200 operational configurations on the San Francisco-Honolulu routes, then plotted the relationship between RPM and manifold pressure. The results showed that reducing revolutions from 2,300 to 1,850 revolutions per minute at 10,000 feet saved an average of 16% in fuel, while reducing speed by less than 3%. At the time, that theory had never been taught in any aviation academy. At a meeting at Pan Am headquarters in Miami in 1935, Lindbergh presented his results using hand calculations. A young engineer recalled, "He didn't say much. He placed the sheet on the table, tapped it with a pencil, and said, 'Let the data speak.' That sentence became a slogan within Pan Am's engineering circles, where people began to believe that every number on a gauge was a line of text in the language of physics. When war came, Lindbergh was excluded from military service because of his political stance. But that pushed him deeper into the pure technical world. From 1,941 to 1,943, he worked for United Aircraft Corporation, collaborating with the Chance Vought and Pratt & Whitney design teams. According to the United Aircraft Performance Division report, 1942, Lindbergh participated in R-2800 engine tests on the F-4U Corsair, performing flights lasting more than 8 hours to measure actual fuel use. He recorded every change in mixture and found that merely adjusting it slightly at the auto-lean setting could reduce consumption by up to 20 gallons per hour while keeping cylinder temperatures within safe limits. During the same period, he visited Ford's Willow Run plant, the production center for the B-24 Liberator, to evaluate flight test procedures. An internal Ford report, September 1943, noted, "Mr. Lindbergh suggested the use of fuel consumption charts, instead of pilots' qualitative reports. This marked the first appearance of statistical fuel control in the American aviation industry's product testing programs. He was no longer the hero who crossed the Atlantic, but the mathematician of horsepower, the seeker of truth within dry columns of numbers. In closed lectures at Pratt & Whitney's laboratory, Lindbergh wrote on the board the sentence that would later become his life philosophy: "Specifications are only averages." He explained that all published limits of machinery were merely statistical means, not absolute boundaries. That meant if an operator understood deeply enough, they could exceed those numbers safely. According to him, blind obedience to average data caused pilots to waste energy and designers to miss the true potential of their engines. His way of working always carried the calm of someone who believed in mathematics. A lab employee recalled, "He rarely spoke loudly. He quietly took notes, then later produced a chart. His curve was always lower than the others, that meant lower fuel consumption." When asked how he achieved such precision, Lindbergh simply said, "By respecting every number. In 1942, 1943, the United States reached the peak of wartime industrial expansion. Tens of thousands of aircraft were produced every month, but no one thought about fuel efficiency because oil seemed limitless. Lindbergh saw the opposite. In a letter to the chief engineer of United Aircraft, he warned that, as the scale of war increases, the advantage will belong to those who use data better, not those who produce more. At that time, few understood he was speaking of the future of modern warfare. According to documents from the National Advisory Committee for Aeronautics, NACA 1943, many of Lindbergh's technical proposals on reducing revolutions and optimizing mixture were circulated internally but not implemented due to lack of combat verification. That note haunted him for 2 years. He needed proof beyond the laboratory, and that proof would come in 1944 over the skies of New Guinea, where he brought his entire data philosophy into real combat. In a post-war interview, Pratt & Whitney engineer James Knight said, "He always treated the engine as a living organism. If you listen, you'll know what it needs." That remark evoked the instinct of a man who once lived alone amid ocean clouds for 33 hours. Between mathematics and emotion, Lindbergh chose data as his language, but his attentiveness made him realize that behind every number lay the heartbeat of machines and men. When he left the Willow Run plant for the Pacific in April 1944, his colleagues gave him a small notebook. On its cover was a single line: "Let the numbers fly." Those 3 words, simple yet proud, captured the entire philosophy of Charles Lindbergh flying by data, not by instinct. And a few months later, over the skies of Hollandia, that philosophy would become strategy, a doctrine born from numbers. The first morning in Hollandia began with a thick mist, humidity rising from the tropical forest surrounding the temporary airfield of the 475th Fighter Group. The runway was compacted dirt, with the P-38's tires sinking deep into its surface. Lindbergh awoke before dawn, sitting quietly in his canvas tent, flipping through a small notebook filled with tables he had compiled at Willow Run. "This is data from another world," he thought, then set his pen to the page and wrote on the first line, "Field Test, Hollandia, June 1944. As the sun rose, he walked to the maintenance area, where soldiers were wiping oil from the wings of Silver Lightnings. According to the 35th Fighter Squadron's journal, at 6:10 a.m., he was assigned to fly with Captain Walter Miller, the first test flight by a civilian within a combat formation. The mission was simple: follow the Humboldt Bay coastline, climb to 12,000 feet, and measure fuel consumption under standard cruise conditions. In Lindbergh's notes, he set the engine at 2,200 revolutions per minute, 32 inHg manifold pressure, and an auto-rich mixture. After 1 hour and 40 minutes, the fuel gauge dropped faster than expected. Upon landing, he compared his flight log to Lockheed's technical chart. Actual consumption exceeded theoretical values by 18 to 22%. Factory data underestimated real drag and the effects of tropical climate, he wrote. These figures marked the first discovery, an error margin large enough to explain why many aircraft ran out of fuel hundreds of miles from base. From that day forward, he began measuring everything. While the pilots slept, Lindbergh sat in the technical shack, hand-recording each variable: startup time, climb rate, cylinder head temperature, and remaining fuel. Each diary page contained a dedicated column labeled RPM, MP, OAT, cheat, gal used. According to a surviving copy of his logbook now held at the National Air and Space Museum, he conducted 12 test flights in 2 weeks, recording over 30 parameters per mission. It was the first real combat dataset on the P-38's efficiency under Pacific conditions. No factory engineer had ever gathered such detailed operational data. One rainy afternoon, Lindbergh returned from a 6.5-hour coastal patrol along New Guinea. When the maintenance crew measured his remaining fuel, they stopped and stared at each other in disbelief. 210 gallons left, wrote Technical Sergeant James O'Neill in the report dated the 1st of July 1944. Other lightnings on the same mission had returned nearly empty, with some forced to make emergency landings at auxiliary fields. At that moment, no one understood why Lindbergh's plane was different, only that it came back safely, with enough fuel to fly another 90 minutes. MacDonald, the squadron leader, began to take notice. According to a recorded internal meeting later cited in the 475th Group Operations Report, he asked bluntly, "What did you do differently from us?" Lindbergh replied calmly, "I trust the instruments, not habits." He produced his small notebook, flipping to the 12th page, filled with rows of numbers and hand-drawn graphs. His consumption curve fell so far below Lockheed's standard that MacDonald ordered the technical crew to recheck the fuel gauges. The results confirmed. Everything was working perfectly. Lindbergh kept flying, recording, and the numbers became increasingly clear. Over the next 4 sorties, his average remaining fuel hovered around 200 gallons. According to the 9th Air Force Technical Section, this represented an overall 25% reduction in fuel consumption. That data began to silence the younger pilots. They called him the efficiency man. On the evening of July 3, as oil lamps flickered in the dim mess tent, MacDonald decided to hold a field technical briefing. The room was an old thatched storage hut with a dirt floor and a few makeshift tables and chairs. A grease-stained operations map hung on the wall. Pilots from squadrons 431, 432, and 433 crowded together, flight suits dusty, the air thick with the smell of gasoline. Lindbergh entered carrying a chalkboard. He did not speak of war, he spoke of numbers. On the board, he drew 2 curves, one for standard cruise settings, one for his proposed configuration. The gap between them represented the fuel saved. "This isn't theory," he said. "This is real data. These numbers come from the missions I flew with you." Silence followed. As Captain Merrill Smith later recalled after the war, "We watched him draw, then looked at each other. No one wanted to believe it, but no one dared to argue. He had proof." Lindbergh pointed to the note beneath the chart listing the RPM, manifold pressure, and cylinder temperature values. "The manual says exceeding these ratios will damage the engine," he said. "But I've done it many times and no cylinder failed. Maybe the manual is wrong." It was one of the rare moments in U.S. military history when a civilian challenged official doctrine with field data. There was no argument, only quiet, and the soft sound of rain tapping the thatched roof. MacDonald stood, walked toward the board, studied the final line of numbers, then turned to the others. "We'll try it." That short sentence ended the meeting, but began a new era for the entire group. That night, in a tent heavy with the smell of oil, Lindbergh wrote a report for the United Aircraft Office. He opened his notebook and wrote the final line: "Observed discrepancy between manual data and field results confirmed. True efficiency exists beyond specification." As he put down his pen, he heard distant thunder fading, the rain easing, and the cooling engines outside breathing rhythmically like a giant creature. In that moment, amid the tropical rainforest, data had taken shape, and no one yet realized that from those numbers, a revolution was being born. On the 5th of July 1944, Dense fog blanketed the forested hills around Hollandia, and the ground was soaked from the night's rain. Inside a small hut, Lindbergh spread a flight map before MacDonald and the technical command group. Holding a piece of chalk, he wrote on the wooden board, 2,200 revolutions per minute, 32 inHg, auto, rich equals 100 gallons divided by hour. The room fell silent, with only the faint hum of the generator outside. Then he wrote the second line, slowly and steadily, 1,600 revolutions per minute, 30 inHg, auto, lean, equals 70 gallons divided by hour. According to the internal record of the 475th Fighter Group, this was the first official presentation by a civilian on methods of fuel conservation under combat conditions. Lindbergh explained in a calm, resonant voice, enunciating each word. According to him, maintaining high revolutions during standard cruise did not actually increase true airspeed, because aerodynamic drag and engine thermal load reduced overall efficiency. By lowering revolutions to 1,600, stabilizing manifold pressure at 30 inHg, and setting the mixture to auto-lean, the engine achieved a more efficient combustion ratio, both saving fuel and reducing wear. He said, "Power doesn't lie in the roar, but in stability." Lieutenant Merrill Smith recorded that sentence in his flight logbook. According to the technical data of the Lockheed P-38 Jules, the Allison V171089 engine had a rated power of 1,425 horsepower at 3,000 revolutions per minute, but Lindbergh calculated that at 1,600 revolutions per minute and 30 inHg manifold pressure, the engine still produced 52% of its power while consuming only 70 gallons per hour. The efficiency reached 2.6 miles per gallon, nearly 40% higher than training standards. The pilots stared at the figures as if they were witnessing magic. Some frowned when he mentioned the term over-square, a condition where manifold pressure exceeds revolutions per minute, long considered taboo in flight training. "If you do that, the engine will blow," Lieutenant Wade Lewis objected. Lindbergh simply replied, "I've tried it. It doesn't." The test began the very next morning. Two P-38 Jules aircraft, serial numbers 44 to 23689 and 44 to 23704, were assigned to Lindbergh and Smith. According to the plan, they would fly from Hollandia to Mindiri, loop back along the Atape coastline, a total distance of over 600 miles. Lindbergh set the RPM at 1,600, maintained 30 inHg manifold pressure, and an indicated airspeed of 185 miles per hour. According to the 5th Air Force Technical Flight Log, the 6th of July 1944, during the 6-hour 10-minute flight, the cylinder head temperature of Lindbergh's P-38 never exceeded 220 degrees Celsius, which was 18 degrees Celsius lower than the average mission temperature. Oil pressure remained at 85 pounds per square inches, well within safe limits. When he landed, he still had 205 gallons of fuel remaining. Smith, flying the same route, had only 50. The data was immediately rechecked. The maintenance team removed spark plugs and inspected the cylinders. No cracks or burn marks were found. According to internal reports from the Allison Engine Division, no sign of detonation or pre-ignition observed. This completely overturned the long-held over-square equals dangerous belief that had persisted since the 1,930 seconds. In the following days, MacDonald authorized 4 additional pilots to test the method. Results were consistent. Average fuel consumption dropped 25 to 30%, and flight range increased by 150 miles compared to previous standards. On July 10, the entire squadron gathered in the briefing hut. Lindbergh pinned his chart to the wall. The consumption curve sloped downward. The temperature line ran flat. He said, "This isn't a trick. It's mathematics." According to Captain Merrill Smith's later recollection, the room then was filled only with the sound of rain and the tap of his pencil on the wooden table. The pilots began to realize that this data did not come from theory, it came from real-world experience. When the method was applied more broadly, the difference became unmistakable. According to the 9th Air Force Technical Report, July 1000, 944, missions of the 475th Fighter Group using the Lindbergh settings achieved an average combat radius of 750 miles, a 31% increase over previous figures. Some bomber escort missions lasted 9 hours, covering more than 1,000 miles. Areas once beyond the operational range of the P-38 became regular targets. Tactical officers began referring to it as the fuel efficiency doctrine, a doctrine not issued by the command but established by a civilian in the midst of war. According to Lieutenant Colonel MacDonald's memoir, it was the first time he felt that an abstract concept like energy efficiency could save human lives. Before every takeoff, he remembered Lindbergh's words, "Keep the revolutions low, keep the pressure steady, let the airplane breathe." Data was no longer lifeless numbers, it had become a means of survival. When squadrons returned from long missions and saw their fuel gauges still above the green line, they understood they were witnessing a fundamental shift in tactical thinking. By late July, the entire group adopted the new flight regime. A supplemental training order was issued. Cruise at 1,600 revolutions per minute, 30 inHg, auto lean. Maintain 185 IAS. Report any irregularities. Not a single malfunction was recorded. Engineers at Lockheed in California received field reports and revalidated the results. According to a classified cable dated the 28th of July 1944, they confirmed, field data consistent and safe, recommend formal adoption. By the end of summer, Hollandia had grown quieter. Missions became more efficient, with fewer losses. During dinner in the command tent, MacDonald lifted a cup of cold coffee, glancing toward the table where Lindbergh continued filling his statistical charts. He quietly said to Smith, "We've flown by data, and this war just changed." Outside, the sound of P-38 seconds taking off merged with the evening sky, a rhythm steady as a heartbeat. And in that moment, a new doctrine was born from intuition to data, and finally, to belief. In July 1944, Hollandia became the center of an unprecedented phenomenon in the U.S. Air Forces. After the 1,600 revolutions per minute, 30 inHg, auto lean technique was successfully implemented at the 475th Fighter Group, other squadrons in the region began to take notice. Fuel consumption reports from squadrons 431 and 433 indicated an average savings of 25 to 30%, according to the 9th Air Force Technical Review, July 1944. Those figures spread through internal communication channels like an electric current, moving faster than any administrative order. In less than 2 weeks, pilots from the 49th Fighter Group at Bayak and the 8th Fighter Group at Nadzab began testing Lindbergh's method. The spread of data did not come through paperwork but through field experience. A pilot from the 433rd later recalled after the war, "When we landed with fuel to spare, the mechanics at the next base didn't believe us, so they tried it." At each airfield, a single successful flight turned numbers into persuasion stronger than any command. According to records at the Air Force Historical Research Agency, by mid-August 1944, at least 6 units under the 5th Air Force had officially adopted the Lindbergh settings for bomber escort and long-range patrol missions. However, the expansion was not without resistance. At the 5th Air Force Administrative Headquarters in Brisbane, a group of technical officers expressed concern that operating in over-square conditions could cause engine damage if widely implemented. An internal memo dated the 14th of August 1944 described a heated debate between conservatives and supporters. One lieutenant colonel opposed it, saying, "A civilian cannot redefine military procedures." But the impressive figures from Hollandia weakened that argument. The third-week August report showed that squadrons applying the new technique had increased their average flight duration from 6 to 8.5 hours, reduced mechanical failure rates by 12%, and nearly eliminated losses due to fuel exhaustion. MacDonald submitted a summary to headquarters, stating, "This method has proven both effective and safe across more than 100 missions." According to the 475th Group Operational Report, August 1944, There were no cases of engine damage from applying Lindbergh's settings. Under the weight of data, skepticism turned into approval. In early September, the 5th Air Force Tactical Engineering Office requested Lindbergh to personally revise the instruction tables for standardization across the region. In a makeshift office at Hollandia, he sat at a wooden desk surrounded by piles of documents and charts. Outside, rain fell on the palm canopies. Lindbergh adjusted each number, cross-checking it with field results. He rewrote the entire cruise settings table for the P-38 Jules, adding a new annotation column, recommended by C.A. Lindbergh, civilian consultant. It was the first time in U.S. Air Force history that a man without rank was authorized to modify official wartime training documents. According to the 5th Air Force Technical Bulletin, October 1944, the new charts were printed and distributed to every base. The line at the beginning read, "Field-proven adjustments have demonstrated a 31% increase in operational radius." At the bottom was the signature of Major General Ennis Whitehead, the operations commander. He approved it without consulting Washington, a decision considered a break from administrative precedent. Some officers later recalled Whitehead's brief remark during the meeting, "If it saves fuel and saves lives, it's military enough." From that moment, Lindbergh's technique stepped beyond personal practice to become an official operational doctrine. Regular training sessions at bases in New Guinea, Morotai, and Biak all began with the presentation of the new consumption charts. Pilots learned to read RPM and manifold pressure as a tactical language. Instead of flying by instinct, they flew by data. According to the USAAF Operational Analysis Division Summary, November 1944, the region's average fuel consumption dropped from 97 to 70, 2 gallons per hour, and cruise efficiency reached 2.5 miles per gallon. At the same time, in Washington, the Army Air Forces Command began to take notice of the Hollandia phenomenon. A summary report sent to the Air Technical Committee stated, "A civilian field consultant has achieved a statistically verified improvement in range performance across multiple squadrons." That report became the foundation for defining the concept of operational data transfer, the direct integration of individual field data into combat training procedures. According to military historians, this marked the first time in history that knowledge from the field was institutionalized within the command system. The event carried not only technical significance but also political implications. Roosevelt had never revoked the order barring Lindbergh from military service, yet the very man once banned was now shaping Air Force operations. When copies of the report reached the War Department in October 1944, no one could deny that combat efficiency had clearly improved. The door between civilian and military worlds had opened just a crack enough for knowledge to pass through. As Colonel Warren Lewis, commander of the 432nd Squadron, recalled, "We learned that sometimes data is an order stronger than a general." He remembered the morning his squadron flew 900 miles to the target at Halmahera and returned with more than an hour of fuel to spare. That feeling, he said, was like seeing the war with new eyes. When Lindbergh left Hollandia in August, he left behind not only a table of figures but an entire way of thinking. From then on, every pilot in training was required to understand the relationship between RPM, manifold pressure, and fuel, the triangular axis of survival. In war, data had become a weapon, and in the Pacific, the first man to wield it was not a general, but an engineer who knew how to listen to engines and turn their sound into numbers. In early 1945, as the war in the Pacific entered its final phase, the last copies of the 5th Air Force Technical Bulletin were sent to Washington. In its appendix, a note read, "Fuel Economy Procedure, P-38 Jules, recommended cruise settings by C.A. Lindbergh." Those small lines were later copied almost verbatim into the USAAF Pilot's Training Manual for the P-38, Chapter **9, Fuel Management. According to the February 1945 edition published by the Government Printing Office, this was the first time the concept of lean cruise was formally codified in a United States Air Force training manual. The accompanying charts clearly illustrated the consumption curves in 3 regimes: standard, economy, and lean of peak. A note at the bottom stated, "Field data verified by operational results in the Southwest Pacific." This standardization was more than a technical step. It was official recognition that a principle born in the field had been accepted at the strategic level. By mid-1945, every pilot trained on the P-38 or P-51 was required to learn the new fuel management procedure and understand the relationship among RPM, manifold pressure, and mixture. They learned to fly by data, recording fuel consumption in real time, something never before included in flight training. According to a report by the Air Training Command, by August 1945, more than 7,200 pilots had been trained under the new program. When the war ended, the engineers who had served in the air forces carried that philosophy back to the civilian factories. Lockheed, Boeing, and the Allison Engine Division began converting their production lines for commercial aviation. According to a Lockheed internal memorandum, September 1945, the company's engineering team used findings from the Hollandia report to reanalyze the fuel consumption curves of the Allison V1710 engine. They found that Lindbergh's model could be extended to all liquid-cooled piston engines. At the same time, the team at Allison proposed applying the optimum efficiency envelope principle to the J-33 jet engine used in the P-80 Shooting Star. According to Allison's 1946 technical record, the same logic of balancing fuel flow and compressor pressure improved turbine durability by 18% and reduced average combustion chamber temperature by 25 degrees Celsius. This demonstrated that Lindbergh's method did not stop at piston engines, but had evolved into a comprehensive principle of energy regulation. Young postwar engineers called it the Lindbergh equation. Not a mathematical formula, but a way of thinking, that every mechanical system possesses an optimal point between power and consumption. In civil aviation, the principle of lean of peak operation became widespread by the late 1942. According to the Cessna Pilot Operating Handbook, 1948, running Continental engines in the lean of peak mixture reduced fuel consumption by 15 to 20%, and extended spark plug life to 400 flight hours. Piper applied a similar procedure to the PA-24 Comanche line. Flight schools began training new pilots in Lindbergh's philosophy, not to fly by instinct but by measurable data. Alongside its technical influence, the philosophical impact spread as well. In the U.S., Air Force strategic officer training programs between 1947 1949, the document Operational Analysis, Efficiency and Range Management was included in the official curriculum. The report directly cited the 5th Air Force Fuel Study, 1944, asserting that victory in air combat came not only from firepower, but from the ability to sustain energy longer than the opponent. As General Karl Spaatz stated, "Firepower wins battles, but efficiency wins wars." That statement became a new axiom of post-war American air doctrine. In industrial factories, the principle quickly spread beyond aviation. At General Motors, engineers who had worked at Willow Run introduced the concept of statistical performance testing, derived directly from Lindbergh's method of collecting field data. Ford Motor Company later incorporated the approach into civilian automobile production lines, marking the beginning of the quality control revolution, the foundation of modern quality management. According to the War Production Board, it was technicians from the air forces who brought performance measurement thinking back to civilian industry, creating a systemic transformation. Academically, the Society of Automotive Engineers, SAE, published the paper Fuel Efficiency Techniques in Military Aircraft in March 1946, citing Lindbergh's notes and the Hollandia report. The article concluded that a deeper understanding of the fuel mixture mechanism was the first step in bringing aeronautical science into the data age. From then on, the term fuel efficiency doctrine appeared in professional conferences, symbolizing the transition between wartime field experience and industrial science. On an ideological level, America entered a new era of technological power. The war had taught the nation that victory was not defined by firepower alone, but by resource management. From the hand-drawn charts at Hollandia, An operational doctrine was born, one that shaped the mindset of future engineers. Lindbergh, once expelled from the military system, was now regarded by technical schools as a symbol of empirical methodology. According to the U.S. Air Technical Service Command Summary, 1947, the lessons from field efficiency research directly influenced the post-war industrial design philosophy. That sentence was framed on the wall of Lockheed's research facility in Burbank. Each morning, young engineers walking past it would read the final line of the quotation, "From power to precision." It was the spiritual legacy of the post-war era, when Americans began redefining combat effectiveness from firepower superiority to operational efficiency, and from that moment on, the entire industrial world learned to listen to the voice of data. When the Pacific War ended, most of the pilots of the 475th Fighter Group had left New Guinea. The P-38 Jules aircraft that once took off from Hollandia now sat motionless in their hangars, their bodies coated with salt dust. But within the reports and charts sent to Washington, a new doctrine had been born. Before the world ever knew the term data-driven warfare, Lindbergh had already proven that empirical data could defeat dogma. He used no authority or rank, only handwritten tables and figures gathered on the battlefield to show that precision could save lives. According to the postwar evaluation report of the U.S. Army Air Forces, 1946, engineers at Wright Field described the Hollandia case as the first operational example of data-led doctrine. They recognized that the U.S. Air Force's victory did not come from a new weapon, but from its ability to convert individual experience into training procedures. Lindbergh's philosophy observe, measure, verify became the foundation of modern military organization. He transformed flying skills, once based on intuition, into a quantitative science. After 1945, Britain and the United States began collaborating in a new field called operational research, a scientific discipline using data analysis to optimize tactics, originating from Britain's radar experience during the Battle of Britain. Yet, in a 1947 Anglo-American cooperation report, a small footnote read, "Early field data integration experiments were successfully demonstrated in the Pacific Theater, notably by civilian consultant C.A. Lindbergh." That note was an acknowledgement that Lindbergh's principle had paved the way for operational research, an empirical, evidence-based approach, rather than one built on assumptions. His influence went beyond engineering. According to Rand Corporation's 1948 archives, the standardization of the lean cruise technique in pilot training was considered the earliest example of knowledge transfer from field to doctrine. The data tables collected at Hollandia were later used as teaching materials for ISO, officer training programs in operational research at the California Institute of Technology. There, instructors recreated the RPM fuel flow airspeed graphs to explain the concept of system efficiency, a term that would later form the foundation of industrial control theory. Professor Philip Morse, who led wartime research at MIT, remarked, "Lindbergh proved that empirical data not only improves performance but reshapes the way humans make decisions." He described Lindbergh's actions as a numerical rebellion against bureaucratic procedures within military institutions. From that spirit arose many post-war initiatives, such as Project Scoop and the Statistical Control Division of the Air Force, founded on the belief that every strategic decision must be grounded in field evidence. From a systemic perspective, Lindbergh's impact reached far beyond technology. He demonstrated that a massive organization like the U.S. Air Force could learn from outsiders and learn faster when data was not blocked by hierarchy. This event laid the groundwork for civil-military collaboration models in the early Cold War era. When research institutions such as RAND, MITRE, and the Boeing Scientific Division were established in the late 1942s, the first principle they adopted was open data exchange, a mechanism allowing civilian experts to participate directly in strategic planning. That spirit originated from the experience of 1944, when an outsider was permitted to redefine the way an entire force flew. According to Air Force Historical Study number 120, 1950. The long-term effects of Lindbergh's technique appeared in two ways. First, the average fuel consumption rate of all U.S. fighter aircraft during 1944-45 decreased by 27% compared to the previous year. Second, in the post-war era, the efficiency mindset influenced jet aircraft design. His principles shaped the range-first design philosophy of Lockheed and North American, the manufacturers of the F-80 and F-86, the mainstays of the Cold War. Technical scholars later called this the Lindbergh paradox. A man cast out of the system ended up making the system smarter. As noted in the Journal of Military Science, 1952, the lesson from Hollandia did not lie in the RPM formula or range charts, but in an organization's ability to listen to data. The authors wrote, "An institution survives not by authority, but by learning." That line encapsulates Lindbergh's deepest legacy, the capacity to learn from reality, even when the bearer of that reality holds no rank. This philosophy soon extended beyond aviation. When NASA was founded in 1958, many engineers with Air Force backgrounds applied Lindbergh's principle of field verification to the X-15 test flight program. In the Flight Test Engineering Manual, they wrote, "Every chart begins with a pilot's observation." That note served as a reminder that every technological breakthrough begins with an individual daring to question the numbers. Half a century later, as modern aviation entered the computer age, the fuel flow optimization algorithms of the Boeing 787 and Airbus A350 still carried the spirit of Hollandia 1944. Flight performance simulation programs trace their lineage back to the formula 1,600 revolutions per minute, 30 inHg, auto-lean, 185 miles per hour IAS, now rewritten as an equation within automatic flight management systems. According to Boeing's 2016 technical report, applying economy cruise settings reduced fuel consumption by 3.5% per flight, a small figure, but the outcome of a legacy spanning over 70 years. When asked about the value of those old datasheets, a former 475th pilot said in a 1970 interview, "We didn't know we were doing something great. We just saw him measure everything and somehow we flew farther." That sentence captured the spirit of the data age, turning experience into knowledge and observation into policy. From the simple numbers at Hollandia, a philosophy of wartime management was born, the belief that true power belongs to those who know how to measure the world around them. And when the pilots of the 475th looked back on 1944, they all said the same thing. The P-38 Lightning became untouchable, not because of its speed or firepower, but because they had learned to understand every gallon of fuel, every number, and every limit of themselves.